Hi, welcome back to Perceive 2021. While machine learning models have been with us almost a decade, testing of these models and comparing their performance remains a challenge. Fortunately, today we have Eric Nelson, Chief Technology Officer at MORSE, to discuss the test and evaluation of machine learning models today and into the future. Eric, stage is yours.
Great. Thanks a lot, Pablo. My name is Eric Nelson, the Chief Technology Officer for Software here at MORSE Corp. First thing I want to do is thank Clarifai for inviting me to this Perceive conference. Very excited to be a part of this event. In here, I'm going to be talking about test and evaluation of machine learning models using Charybdis, and I will talk about what Charybdis is. But first, I'm going to talk about what MORSE is and who MORSE is. So MORSE is a small for-profit business in Cambridge, Massachusetts. We do defense contracting. I'm going to read our mission statement real quick here. So MORSE is a specially selected team of scientists, engineers, and software developers who use asymmetric and unconventional approaches to deploy practical solutions that solve difficult multidisciplinary problems faced by the U.S. national security ecosystem. So not only does this include AI and ML, but we do a lot of autonomous systems, physical systems, a lot of software, et cetera. But with all the systems that we've developed require a lot of testing. How do you know it works? How do you know it adds value to the end users? So I'm going to be talking about all of that today. So going back to artificial intelligence and machine learning. So looking at a typical life cycle of a machine learning project, and I'm going to be using machine learning and artificial intelligence interchangeably throughout this talk. I primarily mean machine learning, but they can obviously be interchanged depending upon your definitions. These are basically systems that do inference upon data. Anyways, so this is a cycle, but usually we would start with data preparation, get your data ready, and then train upon it, make a nice machine learning model that can understand and make extrapolations based upon what data it has seen. Then once it does that, you have to do test and evaluation. Does this model actually work? Then you deploy it. And then based on what you deploy, then you can collect more data, train new models, test and evaluate, and iterate. You always want to iterate, see what works, see what is better. So I'm going to focus upon test and evaluation in this talk. So there's several different types of machine learning models. I'm going to talk really briefly about computer vision, natural language processing, and time series forecasting. That said, this presentation, or specifically the examples given in this presentation, focuses on computer vision. That said, they work for almost all types of machine learning, but I wanted to focus the talk just to be concrete enough and not make it so generic that it was hard to follow what I was saying. So computer vision is basically looking at either still imagery or video, which is moving imagery, and trying to find things that detect things, track things, do segmentation, be like, is this a person? Is this a dog? Is this a red light, green light? Is it a stop sign? And you can obviously be correct or incorrect on these. And obviously with this, humans have a very advanced vision systems. Most animals have a very advanced vision systems compared to what computers can do, though computers are rapidly catching up. Next is natural language processing. This is taking language and basically looking at text data and summarizing it, translating it, doing what humans usually do, but simplifying it, maybe even creating new text. And there's been a lot of advancements in that in the past several years. And then finally, time series forecasting. The classic thing here is weather prediction or even stock market prediction. Which way are things going to go based upon time series data? That said, I'm going to be focusing on computer vision for the rest of this talk. So topics going forward, I'm going to talk about the testing pyramid, the different things that can be tested, some sample metrics, sample results, and then finally go over some best practices depending on how much time I have remaining at the end of this presentation. So first here is a test pyramid. Several people who have done software development in the past should be familiar with the concept of a test pyramid, at least with the unit testing being on the bottom and then integration testing on top of that. The several layers above that, I have customized for this presentation to be focused upon AI. Other testing for software usually focuses more upon user interface, which is also relevant in these situations. I'm going to focus on the AI side. So the first level of this is algorithm testing. So we want to isolate our algorithm, see how it works in a very well-controlled environment. With that, we can usually scale testing, like run it on the cloud, run it against thousands to millions of images very rapidly. Whereas if it's a computer vision system, normally you would run it in real time, and 30 seconds of video would take 30 seconds, and days worth of video would take a day. But if you can parallelize things in algorithm T&E, you can do a day's worth of video testing in a minute, just by using more and more computers, more and more compute at it. Next up is system T&E. So system T&E is taking your algorithm and integrating it with the rest of the system, the rest of the software, the rest of the hardware, and see how the algorithm behaves. Does it still behave the same way you expect it to behave when it was just the isolated algorithm? Does what you want the user to see, is that actually available? In like a real-time system, you'll find a lot of real-time constraints in there. So you'll find a lot more issues in your system as you integrate more and more of it. And then finally, there is operational testing. Operational testing, I would say, is certainly the most important. I mean, they're all very important, but operational testing is where you actually sit down with a user. It's the same as system T&E, except it also has an actual end user. And the question you always want to answer is, does this system add value to the end user? And if the answer is yes, that's great. If the answer is no, you figure out why not. So you always want to align and make sure the results of operational testing match the results of algorithm testing. And if the operational test results don't match, then you need to change what you do in algorithm testing. Because just like the customer is always right, the user is always right. We want to make sure this adds value to the user. And you always want to, any lessons learned, every time you meet with a user, you learn something different, something you hadn't thought of. And is there a way you can build these lessons learned into system T&E or into algorithm T&E, into the earlier parts of your process that tend to run faster? All right, next up, look at the testing pyramid in practice. So this is a computer vision, an image of a computer vision system here. The left-hand side is the system, the left-hand side of this diagonal dashed line, and the right-hand side is the metrics one can use to measure the effectiveness of a computer vision system. So in a typical computer vision system, you have your sensor, which is a camera. That's just like grabbing images, grabbing video. And then first step is typically to put those images into a detector, which is usually a deep neural net, which famously started with ImageNet being so successful about 10 years ago, and says, like, what can it detect from a still image? And there are various metrics that are used for that, MAP and PR curves, which I'll go over in a few slides. Then there is a confidence filter, which is a typical next step, which can be measured using precision recall F1. I'll go over those in a few slides. Then there is a tracker, which is how you take detections from a single image. Like if you have a still frame of a dog and you want to turn that into a video or a track of a dog, you need to connect all of those still detections across frames. And a metric for that would be track fragmentation, average track accuracy, or the various MOTA metrics. And then finally, you would put all these into a database and show them to a user with a user interface. And these, the metrics I put TBD here, this is to be determined, because operational metrics tend to be customized for the operational scenario. So whatever problem you're trying to solve, whatever value you're trying to add to the user should be measurable by some way that's different from the metrics listed above. All right, so I guess before I go into details on what those metrics are, there are several T&E capabilities that MORSE has developed over the years that help us kind of do a lot of these metrics out of the box. The first is Charybdis. This is computer vision focused, but not doesn't work only for computer vision. But this basically calculates metrics on a single video or a single set of images. Like it'll calculate precision, recall, look at your labels, compare them to the inference results, and see what is good, what is bad, etc., based on a single video. Then there is Metal, which instead of running on a single video, it takes Charybdis and scales it to hundreds and thousands of videos all at the same time. So it works with Spark, works on clusters of computers, and can do many things at once. Then there's Proctor, which does a scheduling of your model. So when somebody will submit a model for test and evaluation, Proctor is what runs it through Charybdis, runs it through Metal, and tells everything to go and gives a thumbs up, thumbs down, runs the various levels of testing. And then finally, there's Gradient, which generates a report based upon the results from Charybdis and Metal. All right, now I'm going to do a bit of a deep dive into different types of metrics. So I mentioned precision, recall, F1, F beta, etc. So I'm going to do a quick overview of what these are. Again, these also apply for natural language processing type of algorithms. But precision is, let's say you have an image, like here on the left, let's say you have an image and it has 3 dogs and 4 cats in it. And you have a model whose job it is to detect dogs. In this case, everything within the circle here on the left were detected as dogs. Of those 5 things that were detected, 2 of them actually were dogs and 3 of them were cats. So precision is true positives, which is the correct dogs, divided by total number of detections, which in this case is 5. So 2 over 5, that means your precision is 40%. In other words, of the detections detected by this model, you'd expect 40% of them to be correct. That is precision. Next up is recall. So recall, again, say you have a dog detector. This is basically telling you how many of the dogs in the image were successfully detected. Here on the left here, we have 4 cats, 5 dogs. And of that, 3 dogs were detected and 2 were detected as cats. We talked about that with precision. But here with recall, you're looking at how many true positives compared to false negatives. So here there are 5 total dogs in the image, but only 3 were detected by our model and 2 were missed. So this is telling you that our recall is true positives over false negatives plus true positives. So recall here is 60%. That means that 60% of the dogs in the image were successfully identified. So again, precision is how many were correct, and recall is how many were actually identified. So how do you put those 2 numbers together? Because now you have 2 numbers to deal with. So I guess I'll go through another example before putting those together. Is here, say we have 1, 2, 3, 4, 5, 6, 7, 8 total dogs. 3 of them, the one with boxes around them, were detected. So here our precision is perfect because all 3 of the boxes are correct. They really are dogs. But our recall is poor. It's 0.375 or 37.5% because 5 of the dogs were not detected. So precision is perfect. Recall is imperfect. This is great for certain scenarios. Sometimes you want perfect precision at expense of recall. Sometimes you don't. The other example is here's a situation with only 3 dogs, but we have, 8 detections. So these 8 detections, 5 of those detections are wrong. But every single dog in the image was found. So here we have perfect recall. Every single dog in the image was found. So this is reliable if you want to find everything. But the precision was imperfect. So that means someone would need to go through and say, oh, this is wrong, this is wrong, this is wrong. So here This is perfect recall, imperfect precision. So again, there's a trade-off between precision and recall. What do you actually want to do? Depends on what your users want, what your users need is how you would train your model. So then putting those two numbers together, precision and recall, are typically combined with what's called an F-score, also known as F1, which is the most common F-score, which evenly weights precision and recall together. This is a harmonic mean. For all the math majors out there who understand what a harmonic mean is, great. For everyone else, just understand it's basically an average between the two. But if one is much smaller than the other, then it's weighted towards a smaller number. So here the precision is 375, recall is a perfect 1. The harmonic mean of those two is 54.5, which is closer to the lower number. And with a 54.5 F-score, F1 score, you get a good idea of how accurate this system is. All right, next up, I'm going to talk about precision and recall curves and talk about the trade-off between precision and recall. So with a single model here, it is common to have, I talked about a confidence threshold earlier. Looking at the rightmost box here with a confidence of 0.2. So if you have a very low confidence threshold, your model is going to output tons and tons of the text. It's like, this might be a dog, this might be a dog, I'm not sure. And if you accept all of them, your recall ends up being extremely high. You're going to get a lot of false positives, but your recall is extremely high. Your precision is fairly low. But then as you dial up your confidence threshold to 0.4, you see there are fewer detects, to 0.6, even fewer detects, and all the way to the left to 0.8, you have the lowest number of detects where there's only one false positive and two true positives. So with this, you can come up with a curve as a parametric curve as you change the confidence values. What is precision and recall for each confidence value, which comes up with this curve. Precision and recall curves are a very useful way to understand your model. It's a very, I guess, raw look into your model. It's before the confidence filter. It's very early on, but it gives you a good idea of what your data looks like. The shape of this curve tells you a lot about your data and a lot about your model. All right, so next up here is mean average or average precision and mean average precision. On the left side here, AP, average precision. So average precision is defined as basically it's the area under the curve of the PR curve. So looking at all the different values here, for all the different recalls, all different precisions, measure this area, that is your average precision number. Gives you a good idea of how good your model is. An average precision of 1 is perfect. That means that that precision is always 1, no matter what recall is, and 0 would then be fairly poor. Then as things get complicated, we've been talking about just only a single class this whole time, detecting dogs. But say you had a model that detected dogs and cats and here turtles, how do you combine those numbers together? And so if we had an average precision for dog of 0.8, an average precision for cat of 0.9, an average precision for turtle of 0.4, mean average precision, you put those together, you get 0.7. Add them up, divide by 3, that's 0.7. So mean average precision and average precision, precision, recall, and F-score are all very standard ways to measure classification, classification type models to measure how accurate they are. And each of these numbers are also called accuracy. They're different measures of accuracy. All right, next up, I'm going to talk about trag fragmentation very briefly because we're running short on time. So when you're looking at tracks over time, say you're following a dog through a video, if your machine learning algorithm identifies this as Fido for the first minute and then says, oh, wait, never mind, it's not Fido, that's Baxter, and then switches back to Fido again, that is fragmenting your tracks. You're machine learning model is basically indecisive. It's not sure which dog this is. You have fragmented tracks. So with this, we actually have a metric called track fragmentation, which measures how often does your machine learning model fragment tracks. And a lower number is better. One that never fragments is ideal. So going back into the topic of multiple classes. So the first thing is that a general rule of thumb is we want to keep metrics simple for stakeholders, all stakeholders. When we're running Metal Encryptus and all these tools that I was talking about earlier, it generates a lot of data, a massive table. We call it the hypercube. It tends to have millions of rows that even extremely technical folks, like it's too much information for them to understand. So you always want to keep things simple, simplify them, and ideally give a single score for a model. Like this model is a 0.7. Is that good? Is that bad? But you want to be able to compare them against others. So I was talking about precision, talking about recall. Those are two numbers. They can be simplified to one using an F1 score. But then I talk about F1 and talk about track fragmentation. How do we put those together? I'll talk about that in a few slides. But here we have multiple classes, dog and cat. If you're 0.8 on dog and 0.9 on cat, how do you put those together? Well, you can just take a mean of those and have a 0.85 to be your average of those two classes. But then what happens if you add more classes? In this example, we still have dog and cat, which we knew we had 0.85 as a mean. But what if we add bunny and panda and turtle and squirrel and bird? Add a whole bunch more classes, brand new classes, and say the model is not as good as these. Now the mean is at 0.47. Does that mean this is a worse model than the previous model? No, it doesn't. It just means that this mean, this 0.47, cannot be compared to the other mean. So it's always like, you got to be careful with metrics, how you simplify things. There's a lot of nuance that gets lost by simplifying these metrics. That said, there's a lot of detail that is summarized, which is very much appreciated. And then my last example here is, what if you add three more, last minute, like, oh, you submitted a model, we just added three more object classes that you have not yet trained on. You get zeros on those. And now your mean is down to 0.33. And this actually, if your model is trying, if its cost function is to maximize this mean, then your model will get the most reward, the most maximizing of this 0.33 number by training on giraffe, hippo, or elephant. Going from 0 to like 0.3 would be a massive jump. Whereas taking dog from 0.8 to 0.9, or cat from 0.9 to 0.95, which is a whole lot harder, would barely make a dent in this mean. So you always have to be careful about the metrics that you set up for your users to make sure that you are incentivizing the right thing. Because both the humans who are developing these models and just the models themselves, which are training on a cost function, will find the easiest way to maximize a number. So the number you pick is incredibly important to make sure that it's done right. All right, next up, another thing to deal with multiple metrics is sometimes you cannot simply average them. I talked about F1 scores earlier and combining them with track fragmentation. So track fragmentation is very easy to get down to 0 if you never detect anything, or if you only detect one thing and never break your track can be 0, real easy. But then your F score will probably get punished because your recall will be poor, your precision will be poor. So you want both to be good. So in this situation here, we have track frag where lower is better, F1 where higher is better, and our goal here is on the lower right. So looking at these models, which of these models is the best? One could argue A because it seems the furthest to the right, but that could just be the way the axes are skewed. So you can say that A is definitely better than C, because A is to the right of C and down from C. So it's clearly better. But C and D, is C better than D or is D better than C? It's not clear because D is down, has better track frag, but C has better F score. Which is more important to the user? It's not clear. So you have to come up with some kind of way to combine these numbers together in a reasonable way. So here we've generally have had success with just weighing two numbers together in some kind of smart way so it can be clear which is better. So we add these extra contour lines, and using these contour lines, you can see A is slightly better than D, which is slightly better than C. Then E and E is slightly better than C. So like adding these contour lines can add a lot of insight into what's most useful to the user, and normalizing things when possible. All right, so this is I guess a quick review here, the testing pyramid in practice. So went over detector and mean average precision and PR curves. Then once you pick a confidence value, like what confidence value do you want your models to go with? That's when you get precision, recall, and F1. And then when you start tracking, you get track fragmentation. But always, always, always look at what your user needs are. Like that's the really important part. That's what you really want to take away, and really get right. And always iterate, make sure these metrics make sense to your user. Yeah, testing pyramid, already went over this, but hit all of these topics as well. Let's see how we're doing on time. I'm gonna skip over these metrics because no way I would cover those in 3 minutes. There's a couple of best practices I'm going to hit real quick with the 2 minutes we have left. So some best practices in test and evaluation. The first is that operational testing, I would say, is the most important, but it's generally also the slowest for the reasons I discussed earlier. Algorithm T&E, you can scale a lot, and operational T&E tends to run in real time. But you want to push lessons learned from operational T&E earlier and earlier in the process. Next up is automation is key to everything. You always want to automate. When you automate, then you save on human error and things just generally run faster. In one instance for T&E, Morse was able to take a process that was 30 days to T&E a model down to 1.5 hours. And that 1.5 hours gives feedback to model developers very quickly. And they can pivot, you can find problems with your data. It just makes a lot of things easier. Next up is always have computer science drops. At the end of the day, machine learning and artificial intelligence, they're big software programs. So a lot of bugs you will hit during test and evaluation end up just being simple software bugs. So make sure the software is working. Integrate what we call computer science drops. They just test the interfaces, test memory, test all these things, and don't check all the precision, recall, and F scores that I talked about earlier. Next up is if you're doing some sort of competition, try to decide on metrics before model development. The sooner all the developers know what they're going to be measured against, the sooner they can set the cost functions for their machine learning to train on those things. That said, at the same time, you don't want to be stuck with old metrics. You always want to be finding new metrics, finding what makes sense for your users, but not change them so frequently that the developers can't keep up. And then next up, data splitting. You always want to split your data into training sets, validation sets, and test sets, where the models train on the training data, they test internally on the validation data, then the testing set is never shared with the models. It's not even shared with the model developers because you don't want to have any type of overfit on the test data. All right, and with that, I am out of time. So some examples of libraries that can do test and evaluation. There's MORSE's Charybdis that I just spoke about, which is available to the US government. Reach out to Morse. My contact information is in the conference, but there's also MS Coco, widely available, MOT metrics, and VOT as well. And with that, Thank you very much. And thank you again to Clarifai.
Eric, thanks so much for joining us today on our virtual stage. Pleasure to learn about how to best test and evaluate the machine learning models. I really appreciate the best practices. And a big round of applause from our virtual audience. We'll see you at the next session. Thank you.